Thanks for joining today. So I would be talking about the cosmic dawn signal and specifically about the SARAS experiment and its recent results. Before we really dive into anything, this is just a key takeaway, which is a SARAS-3 experiment based on our latest observations has refuted the presence of a flattened profile, which was claimed to be the 21 centimeter signal from cosmic dawn. And basically with this finding, we are bringing back the standard cosmological models that were not sufficient to explain the flattened profile that was detected by the EDGES experiment. And with that, let's dive deep into the nitty-gritties of this specific takeaway. And one step before, a big shout out to entire SARAS-3 members, without which none of this would have been possible, with a lot of support from facilities at RRI. And so yeah, let's dive deep. And sorry if a lot of this audience already know about this, but this is what we are really trying to do here, is to try to detect the neutral hydrogen emission of 21 centimeter radiation from cosmic dawn. And the motivation for doing that is we have a good understanding of what happened when the first atoms formed, thanks to all the CMB experiments like Planck and WMAP. And we have a reasonably good understanding of the local universe based on all the observations in multi-wavelength. But this transition between the first atoms to the current universe is severely unconstrained just because of the lack of observations. And cosmic dawn really forms one of those parts. So this is the part that happened around a few 100 million years after the Big Bang, when the very first sources of radiations formed. And the ionizing radiation that they emitted ended up ionizing the entire universe. So basically cosmic dawn, which was followed by epoch of reionization. And one of the very important ways to study this is using the 21 centimeter radiation that is that emitted from hydrogen atom. And the best part about this observable is its time information, because its rest frame frequency is fixed, which is 1420 megahertz, and it redshifts as it reaches us. So when we are looking for the signal at a specific frequency, we are probing a very unique redshift in the evolution of the universe. So unlike some other measurements, it gives us a very fine time resolution information about different events that happened over the cosmic history. Now, when we study the 21 centimeter radiation, we can study two different things. One is at a given redshift, we want to probe how the brightness distribution is distributed in the spatially. So basically, if I look at the past, so basically we are on the right side of this plot. And what we are seeing here is the spatial variation, the morphology of the 21 centimeter brightness field, which is governed by a lot of astrophysics that happened during that time, and also the properties of the first stars and the galaxies themselves. But a better and a cheaper way to do that, and these are complementary probes, is to look at the sky average radiation. So instead of looking at the fluctuating component, we look at the mean intensity of the brightness temperature, which is averaged across the spatial direction, and which is what is plotted on the bottom panel here. And you can see that the spectral shape is very rich, and it is actually not variable depending on the astrophysics. So if we are able to measure this mean intensity as a function of redshift, which translates to as a function of frequency, we can constrain a lot of thermal and ionization history of the universe. And with SARAS-3, this is exactly what we are doing. We are interested in computing the mean brightness temperature of the 21 centimeter as a function of frequency. And just to give you an idea of how much of a variation is possible in the signal, this is a very nice movie by Andre Missinger, where on the top panel, we show the brightness temperature field itself. And the next panel, we show the global 21 centimeter signal. And the bottommost panel is the power spectrum, which is studying the fluctuating component and how these changes as we change different astrophysical properties, ranging from the ionization efficiencies to the X-ray properties of the sources, to the minimum mass which is required to form the halos, and so on and so forth. So the idea is basically that once we know what the true signal is, we can reconstruct a lot of astrophysics just based on the nature or the spectral variation of the signals themselves. And just to capture all of this, what we call as the atlas of the 21 centimeter signal, just based on different properties of the cosmic dawn and the epoch of reionization. So this is the motivation for us to be doing such an experiment, because unlike other cosmological probes, we really don't know what the true signal looks like just because of the poor understanding of the first stars. And the way we do it is basically using a single radio telescope. And this is, again, it differs from interferometric observations where we have these arrays of antennas. For global signals, all we need is just a single antenna. And it is certainly not expensive, because what we need is an antenna plugged into a receiver, analog receiver and a digital receiver. And even sensitivity wise, it's not a big limitation, because our sensitivity increases as we integrate more and more data. And we can show that in order to reach the kind of sensitivities that is required, we really need just a few hours in theory. And therefore, really the bottleneck for such kind of experiments comes from the systematics themselves. And really, across all the experiments that I'll be talking about, the systematics are the ones that have limited us in the past from reaching to further better accuracies. So the calibration requirement that we have is really some 1 part in a million in order to basically subtract out all other components in the data and reach down to the level that is required for the 21 centimeter signal. So basically the biggest contaminant is the foregrounds themselves. So when we operate over this frequency range, which is 50 to say 200 megahertz, our galaxy is very bright at these frequencies, dominated by the synchrotron radiation. But at the same time, we have other kind of contaminations that come from the terrestrial emission, basically the RFI or radio frequency interference, and ionosphere. So on the right panel, what you are seeing is just one example of what the foreground brightness is. And you can see it ranges around 1000 Kelvin at low frequencies. And the colored lines are basically the global 21 centimeter signals that we expect just from standard models. And this kind of shows the dynamic range that we require, and therefore the kind of calibration accuracy that we require. These are other challenges, which is radio frequency interference and ionosphere. So radio frequency interference, basically this is the map done from the 70s and 60s Radio Astronomy Explorer, which maps out how bright Earth itself is, thanks to all the transmitters. And just for perspective, around 30 is the level of the galaxy. So really, most of these places are brighter than our biggest contaminations. And ionosphere, of course, has its own processes like refraction, absorption, and emission, which are all frequency dependent and can potentially corrupt the data and confuse us with the actual signal. But really, the strongest constraint comes from our instrument as well. So in order to address the other things, we can go to very quiet radio locations. And this is just a snapshot of what we have done at RRI, which is characterized several sites across India and localized a few good places which are conducive to such observations. And basically the left panel shows the kind of variations we get in RFI once we move from one site to another. And therefore, if you see across the globe, the kind of global 21 centimeter experiments and where they are located, the commonality is the wilderness and the remoteness of the sites, ranging from Karoo Desert right in South Africa to Western Australia, Trans-Himalayas, and Arctics. So that is where we evade at least one of these challenges, which is the radio frequency interference. But the biggest bottleneck is the instrument. So I'd like to always divide these into antenna-dependent effects and the receiver-dependent effects, mostly because, at least in these experiments, we can calibrate the receiver-dominant effects somewhat to better accuracies. But our the calibrations are internal, and therefore all the antenna-related properties have to be very carefully modeled externally and applied onto the data. So basically the primary field of view, the efficiency of the antenna, and of course, as we percolate down the receiver chain, we have our own bandpass transfer functions, followed by different kind of additive components that comes because antenna talks to its environment. So the data that we get comprises all of these effects. And then the idea is to basically separate out all of this and try to reconstruct the 21 centimeter signal. And different experiments have tried to address it in very different ways. So this is just a snapshot of all the different experiments that are trying to do cosmic dawn and EOR using global 21 centimeter signal. And you can see how diverse the antennas are, which is great because then the level of systematics and the shape of the systematics would be different in different experiments. And this is not an exhaustive list. There are several more experiments that are on the horizon, which are very close to commissioning, or they have already started taking the data. So this field is really getting very exciting in coming days when we have more and more experiments coming online. So getting back to the actual part of our talk, which is the absorption feature. So all these experiments, one of the primary science goal is to look for that absorption dip that is shown in the green line. Because as you can see, amplitude wise, this is one of the strongest feature in the 21 centimeter signal. It's theoretically, it is predicted to be around 100 millikelvin or so. And the way it arises astrophysically is that what we are measuring is a brightness contrast between the gas temperature and the background radiation. So what happens is gas is generally colder because it cools faster. And so compared to the background radiation, there is this excess or deficit, which is what gets shown as an absorption. And then as the stars form and the X-ray photons heat the gas and the gas temperature rises above the radiation temperature, we see the rising part of the signal. So essentially, this is basically saying that the gas is cooler in the earlier stages and later it's getting heated up. That gives rise to this absorption feature. And the earlier versions of SARAS had actually placed very strong constraints on these. So this was SARAS 2 that observations were carried out in 2017 and 18 in Timbuktu Collective, which is one of the farms in Andhra Pradesh in India. And based on our observations, we were able to rule out around 10% of the theoretically plausible 21 centimeter signals, mostly the ones that had very deep absorptions. And we went on to actually place limits based on this on the X-ray properties of the first sources. Actually, this was one of the first constraints that came from the 21 centimeter observations. But around the same time, in 2018, we had this remarkable result from EDGE's experiment, which is basically this flattened Gaussian that they had observed, which is shown in panel D here. And this was basically claimed to be the 21 centimeter signal from cosmic dawn. And this was centered at 78 megahertz that corresponded to a redshift of 17. And its amplitude was around 500 millikelvin. So these are the few numbers to take away because in the later parts of the talk, I'll contrast of how it differed from the theoretical predictions. But before we get into that, just a bit about EDGE's experiment itself. So this is located in Western Australia. And it's a flat dipole antenna sitting on a huge ground mesh. So it's basically all metal around it in order to suppress the leakage of the ground radiation into the antenna. And what they found is that the signal profile that they had detected, this flat Gaussian, was robust to several different choices of their hardware, as well as several different choices of the analysis itself. But the problem was that it was very different from what was predicted just based on standard cosmology. So you can see the amplitude of the signal was at least twice the predictions from the standard cosmology. And at the same time, none of the standard models that you see here had any kind of flattenings. And last but not the least, the kind of transitions that you see are very sharp compared to what we saw in the global 21 centimeter signals. So overall, this was a very anomalous detection. And therefore, it really created a huge wave in our community, people trying to provide different kind of explanation of how can such a signal arise, which was sure that no standard cosmology could actually. And you can see that effect just from the ADS statistics. So this basically shows the kind of citations that this specific paper had over a range of years, basically showing the interest in our community. And the kind of papers, they started with dark matter, to radio backgrounds, to systematics, and so on and so forth. But overall, this really got the entire community very excited about the plausible prospects. So the first explanation that was given was to do with dark matter-baryon interactions. So we know the amplitude of the signal is anomalous, which is 500 millikelvin, which essentially means that the contrast between the gas temperature and the radiation temperature is much higher than what we had expected. So how can the gas be colder than expected? One way was, what if it interacts with the dark matter and there is a heat exchange? So one of the theories was that maybe a fraction of dark matter is milli-charged, and that is sufficient to cause this interaction and the heat transfer, which can cool the gas much below what is expected from standard cosmology. But the problem with that explanation was we have very severe constraints on the mass and the charge on the dark matter from the particle physics experiment. So there was a very small parameter space that was viable to explain such a phenomenon. The other explanation went down to the background, which is, let's say the gas is cooler as it should be, but what if the background temperature is hotter than it should be? so that essentially we end up creating the same contrast. And that led to people wondering about what if the background temperature is not just cosmic microwave background, but there are some galaxies in the early universe that really boosted up that power. And again, it led to a lot of fine tuning, but it was very hard because it also had to agree with a lot of local constraints, right? So we have constraints on access on radio, X-rays, and so on and so forth. So if we want to match with them, it was very difficult to create that kind of an access early in the universe. But there was a third possibility, which is what if it's not of astrophysical origin at all? And we, along with several other people in the community, had written papers on it, of how robust the signal detection is based on the choice of the bandwidth, choice of the foreground model, and how unique a solution it is. So what we had shown is that if instead of a flat profile, we replace it with some kind of a sinusoid, it gives as good a fit as the flat profile. And actually a lot of model selection algorithms prefer this model over the flat profile. So there was some bit of analysis papers that basically showed that how the flat profile might not be a unique solution. But all of these was very speculatory, right? So the good way to test this was to basically have independent observations from a completely different instrument, observing at a completely different location. And that's where SARAS comes in. So along with us, there were all different experiments that started off focusing on 50 to 100 megahertz in order to cross-verify what Edge's experiment had seen. And SARAS itself has a range of evolutions starting off around 2010, which is the very first dipole antenna. And with time, it has evolved in its antenna, in its calibration, and in its receiver, and now also the observing environment. And with the current observations, we were able to get down to the sensitivity that was required to cross-verify, which is what I'll come to later in my talk. But before that, the first deployment that we did was really not successful. So just after Edge's results came, we scaled our antennas to operate between 50 to 100 megahertz. And we took it to Trans-Himalayan ranges of Ladakh in India. And we had a run with these two different antennas that are shown here. Both of them are monopole antennas. On the left is basically the different shape of the radiator, which is spherical, and in the right is the disco. And the limiting factor back then was the way antenna was interacting with ground. So as I said before, antenna is also sensitive to the ground radiation, and therefore not just the top surface, but several meters below, because we are observing at meters of wavelengths here. So if the ground has got stratified profiles, there will be these multipath propagation to the antenna, which will imprint a very specific kind of a systematic. And unless we have a very good information about the ground properties and how it changes with depth, it was very hard for us to model these kinds of systematics. So that was really what limited us in cross-verifying this as early as 2018 itself. But then the question was, how do we eliminate the systematics? Or more importantly, what do we really want out of an instrument that observes in such an environment? And the design philosophy of SARAS was that we know that the foregrounds are spectrally smooth, which means that they are almost power law-like, and they can be represented by very low number of terms. While the 21 centimeter signal has these all spectral properties that we saw before. So as long as the instrument response itself does not lead to very fine spectral structures, we should be able to separate out foregrounds along with the instrument contributions from the 21 centimeter signal. So we have basically evolved experiments such that we have electrically small systems with the as frequency independent primary field of view as possible, and the maximally smooth or basically smoothly changing transfer function of the instrument. So with our first deployment here, we were basically not able to guarantee that our own instrument had systematics that were spectrally smooth just because of the ground profile. So we went down and looked for the better alternatives. And the kind of alternatives that we finally saw was lakes. And the reason for choosing them is just the homogeneous medium that is provided by these lakes. So we really have one length scale in the system, which is antenna and the distance between that and the lake bed. And we had basically chosen the kind of depths such that any kind of multipath reflections would not lead to the spectral structures that will confuse us with the 21 centimeter signal. So with that, we went ahead and we redesigned all our instrument, especially antenna, so that it can operate on water and basically operate for very long times. And Therefore, the kind of antenna design was tweaked such that the beam looks slightly up, and it has a mild frequency dependence. And the kind of optimization was done for fresh water, again, in order for our spectral smoothness of the bandpass to hold true. But of course, we cannot measure the antenna properties when we are observing because we do internal calibration. So different properties of these antennas we had to measure before the observations. And I'll skip all of this, basically all the custom measurements that we did to finally show the measurement of the antenna itself. So the two important functions that we require is what we call as the total efficiency, which is shown in the black, and the S11 or the reflection efficiency, which is shown in red. So reflection efficiency determines the kind of spectral structures on the additive, and the total efficiency that is shown in the black determines the spectral structures that are imprinted on the sky, because it's really the fraction of the sky that's coupling to the system. So with all these very fine measurements, 1 part in 10⁶, we were able to demonstrate that the antenna transfer functions are spectrally smooth, which means they don't have these embedded wiggles. Therefore, any kind of systematics or the foreground coupling into the system would not produce the spectral structures that are there in the signal that we are looking for. And the very clear advantage that we can see here is this dot dashed line. This is coming from our ground-based measurement. So you can see that just by going to the lake, which is right here, not that we would just enhance the efficiency, but also smooth out all these finer scale spectral variations. The analog receiver is like a decay switch radiometer. So we have a noise source that we use for calibrating our bandpass, which is followed by a chain of amplifiers and filters. A part of this sits right beneath the antenna, and rest of it sits at the shore, which is separated by 150 meters and connected via optical fibers, again to isolate the antenna part with the rest of the electronics. And especially the front end, which sits beneath the antenna, we have minimized everything so that even if there are standing waves, they do not correspond to the spectral scales of the 21 centimeter signal. And given the remoteness of this experiment, the entire receiver is designed to be operated off batteries. The digital receiver is in-house developed at RRI, and this does 16K point Fourier transform, which gives us appreciable frequency and time resolutions. And this entire system is housed in an electromagnetically shielded enclosure, because this is one of the noisiest systems, which has enough shielding so that the radiation emitted from this does not get into the antenna and basically produce more self-generated RFI. Once we had done the system, we put it together, and before deploying, we had tested it in the lab. So instead of antenna, we replaced it with the terminations or networks that mimic the antenna properties. And we were able to show that using maximally smooth function, which is essentially a function that does not allow any embedded structures, it can only fit to the smooth component of the system response, that we went down all the way to the thermal noise levels, and we could actually acquire millikelvin sensitivities in the lab, which was a validation to go ahead and do the deployments. So the first deployment happened in 2020. And subsequently in March, we had another deployment, so 2 different sites. And the last deployment had actually to be abruptly cut off because of the lockdown that happened due to COVID the very next day. So really kudos to all the team members who had to wrap up at a very short notice and return. But with this data, we had the sufficient sensitivity to do a good science. And fortunately, all of this observation period corresponded to very quiet wind conditions and very quiet ionospheric conditions as well. So I'll very quickly skip over this, but this is all the nitty-gritties of the processing that we do on the raw data. Essentially, it is 2 different stages. One is to calibrate for the bandpass response of the receiver, and then also just flagging RFI, not just at the strong outliers, but the trickiest part is trying to pick up the ones which are very weak and probably broadband. So we ended up throwing a lot of data just because of our flagging itself. As a matter of fact, out of 100 hours that we observed, we have used only 15 hours just because of the very strong flagging algorithms that we have. And this is just glossing over some of the flagging algorithms, and I'll be happy to discuss this offline if people are interested. But the final data basically that we have is spanning over 10 hours to 17 hours in LST. That also includes the galactic center. And based on the RFI conditions, we were able to use 55 to 85 megahertz band, which is slightly shorter than the entire band that was validated in the lab. And we have verified using equivalent simulations for these that we can go all the way to millikelvin noise by following the same pipeline that we have used in the real data. Once we do all of that, we still need 3 finer corrections that are not part of the bandpass calibration. The first is the total efficiency of the antenna, which is what fraction of the sky actually coupled. And the second part is the receiver noise. So the LNA has some noise figure, and that noise basically travels back and forth and creates standing waves, which is what the receiver noise is. So it's an additive to the overall data. And the third contribution comes from the water. Water being at the ambient temperature also couples into the antenna. And so the red line on the right panel shows without these 3 corrections what the data looks like. And the blue is the final data that we have used after applying all these corrections. So this is our final spectrum that we use for analysis. And on the left, and the question that we are asking here is that does this data contain this blue dotted line that is shown here, which is the edges profile? Now, in order to ask this question, we need to first answer what is the foreground and residual systematic model that we want to use on this particular data. So in order to do that, we did 2 different metrics of model selection. One is the Bayesian evidence and one is Bayesian information criteria. And we probed 2 different models. The first model is just a log-log polynomial, which is what people typically use to represent foregrounds. And the second is polynomial along with the edges signal included, which is what we are referred to as joint. And what you see here is the Bayesian information criteria is the lowest for 6th order, and lower the BIC, more preferable is that model. And in all these cases, the polynomial only model is always preferred over a joint model. That itself says that the data kind of refutes the presence of a flattened profile, since that joint model always gets a lower preference. And after this subtraction of this model, the residuals are consistent with thermal noise. So in order to make it more quantitative, we anyway did a joint model of a 6th order polynomial in log-log space, along with a scale factor times the best fit profile. And the idea is if the scale factor is consistent with 0, which means that the data can only be explained just by the log-log polynomial, but the scale factor is 1, it shows the presence of the flat profile in our data. And as expected, what we found is the scale factor to be consistent with 0 at 95% confidence, and therefore rejecting the flattened profile that was seen by the edges experiment. Having done that, the next step is to probe the entire confidence interval that was allowed by edges. And in that, we acknowledge their sharing us with their MCMC chains that spanned over the parameter of the detected signal. So the signal is described by 4 parameters, which is the amplitude, the central frequency, the width, and the flattening. And we basically generated signals that were in the 99% confidence of edges and did exactly the same analysis. And what we found is that the entire set of those parameters were rejected by SARAS. Of course, with different levels of significance, depending on what their amplitude and what their flattening was. But before we actually quote the result, we have to assess our own systematic and statistical errors. So our statistical errors are governed by just the thermal noise that corresponds to 15 hours of observations. And in order to assess our systematic errors, we have done 2 different things. The first question is, how sensitive is our scale factor based on our analysis choice? So we do all kinds of corrections to the data of the total efficiency, the receiver noise. So how much of it really changes if we don't apply those corrections or apply some other version of those corrections? So what you're seeing here is the scale factor that we get over different iterations of the analysis choices. And what we found is basically across these different choices, the scale factor continues to be consistent with 0. So that kind of quantifies this scatter, one source of systematic error. And the other basically comes from looking at how the RMS of the residual itself changes when we go for even higher orders, and basically use that to place a limit on the systematic errors that we might have, though we are consistent with thermal noise all across this. The other part is how sensitive our result is to that specific data set that we have used. So we also do jack times. So we split our observations in 4 different ways. the first half and the later half of the observations, and just the even and the odd time samples. And we again repeat the same analysis. The plot basically shows the residuals that we get from all those 4 different data sets. And again, we find that we are consistent with 0 in all those jack times, basically showing that our results are consistent, not just for specific noise realizations, but different slices in the data. And then in my last part of the talk, I would go down to a very specific question, which is slightly different from finding a flattened profile. So we know that there had been analysis showing that the flat profile was not a unique solution. There was some spectral distortion. So if we fit the edges data that is shown here with just a log-log polynomial, we are not consistent with noise. So there is certainly something more to it. But whether it's a flat profile or it's a sinusoid, they all seem to explain it equally well. So we took a more model independent approach of saying that, okay, if we process the edges data and SARAS data exactly the same way, and we cross-correlate their residuals, what is the kind of correlations do we get? So the question is, does SARAS data have the same kind of spectral distortions that edges data have, without getting into what it could be due to? So on the left, it's a very oversampled version of the SARAS and the edges data, smoothed to around 1.4 megahertz resolution. And we basically cross-correlated these two. So the right panel, black line, shows the cross-correlation that we got out of it. And the 2 histograms basically show us, this is from Monte Carlo analysis, of what the correlation should be. The red showing if there is no spectral distortion, which is common to both. And the blue shows if it's common to both. And again, we find ourselves consistent that the spectral distortion in edges is not seen in SARAS data. And this is actually consistent with around 98% significance. So with that, basically, we have refuted the presence of flat profile or even just the spectral distortions that were seen in edges data. And of course, in this limited time, I cannot go over the entire nitty-gritties, but I would encourage you to all go and check out all these different papers that have come out from the system and also from the analysis. So with combining SARAS-2 and SARAS-3, we have been able to rule out a huge parameter space that was previously unconstrained in the cosmic dawn and epoch of reionization predictions. So all the blue lines that you are seeing are the ones that have been ruled out by SARAS experiment. But you can already see that there is a huge parameter space shown in gray, which is completely unconstrained. And that is what we are targeting next. So that ties up nicely with the next steps of this experiment. So what we have shown now is just with 15 hours of data that the flat profile does not exist in SARAS, and therefore pointing of its non-astrophysical origins. And the same results are obtained when we do cross correlations between the 2 experiments. So we are now trying to deploy this at even more radio quiet locations, mostly in the trans-Himalayan ranges, so that we get more data, which is radio frequency, the interference free. And at the same time, our bandwidth was limited between 55 to 85 just because of the radio environment. So, and if we are able to extend that, we'll probably reach quicker to the sensitivities that are required for the cosmic dawn signals. So those are some of the areas that we are currently working on. And with that, I'll stop and take questions.
Thank you. It was a very nice talk. Thanks. So I just wanted to ask, that scale factor you're talking about, is that for the residual noise?
Let me go to that slide. No, the scale factor is actually multiplied to the best fit edges profile. So essentially our model is a log-log polynomial that represents the foregrounds and systematics, plus a scale factor times the best fit profile. So the free parameters are the polynomial coefficients and the scale factor.
Oh, okay. Yeah, thank you. That is all I wanted to know.
Thanks.
Yeah, I wanted to ask, anyways, I wanted to thank the speaker for the good talk. But I just wanted to ask about something that he said and I've heard before about, you know, how only a single antenna is enough to do the science at like low frequency radio observations. Like, is a single antenna really enough, or is it like just good enough to get the desired results? And is there like zero benefits for having more antennas, or like an interferometry of antennas when observing low frequency at low frequency? I hope that was audible.
Thanks. No, that's a great question. Yeah, so I think we are here talking about the essential requirements. So for global signals especially, this is definitely not true for power spectrum measurements. For global signal, one antenna is sufficient to give us the sensitivity which is required. So essentially, if we just use the radiometer equation, we see with one antenna, we can get down to millikelvin very quickly. Having said that, more antennas are always preferable for multiple reasons. The best part is systematics, which is if one specific antenna in one specific orientation has something going on with the way it's interacting with foregrounds, we can straight away test it with some other part of the antenna. And this experiment has done a wonderful job with that. And the other reason for using more antennas, and Gianni is here, is like LIDA-like programs where you use interferometric observations to model your foregrounds better and actually use that in the single power or total power measurements. So of course, I mean, there are several advantages to using multiple antennas, but just the essential requirement is one is good enough to give the sensitivity that we require.
Good. So yeah, and thank you for the speaker for the very nice talk, and congratulations on the very impressive work. Yeah, and I have two questions. One is you have mentioned the cost correlation, but which two quantities did you cost correlate? I didn't catch up that essence actually. If you could elaborate that again.
So basically, what we are doing here is we took publicly available edges data and SARAS data, and we modeled it exactly with the same foreground model. And the question is, do they have a correlation in residuals? So of course, we have demonstrated with the model that we have adopted that if the spectral distortions are present, we have the sensitivity to detect them. But what we find is that after that model subtraction, we see spectral distortions in edges, which is of course expected given the flat profile. But we don't see the same kind of spectral distortions. Actually, we find no spectral distortion in edges in SARAS data based on the thermal noise that we have. So basically, it's saying that there is no correlation between the spectral distortions.
Okay, I see. And my second question is that given the very distinct results from the two experiments, which aspect in the instrumental part that you think are the major difference, or let's say, could this difference be due to some very fundamental instrumental results?
Yeah, it's really hard to say what exactly might have caused it. But one of the fundamental differences in the two experiments now is really just the observing location and the antenna characteristics. So as I said before, antenna characteristics are almost always modeled externally. So the way we apply for, say, the frequency dependence of the beam is very subjective, and it's probably very model dependent as well. So given the kind of observing environment of SARAS and the fact that it is electrically small with no big ground planes, it certainly has a lot less chromaticity than edges antenna. But beyond that, what really could have caused such a feature in that particular experiment is very hard to speculate.
I see. Just add a last thing. So your main result shows the dip is consistent with 0. Is that what you find? Or if that is true, that's also not a standard model, because there should be some level of depth, right?
Precisely. So with this result, all we are saying is just about the flat profile. So if there is any kind of a signature that resembles a flat profile, we say that corresponding to the scale factor is 0. So all it says is, given our sensitivity, we don't have any flat profiles. But our results does not say anything about the standard models. So if we go back to the plot where we had all of these plotted together, which is essentially this plot, we do not have the sensitivity in SARAS 3 data to get down to the levels of the standard signals and try asking which of them might be there. And that is precisely our next aim of the deployment, to go beyond this flat profile exercise and get down to the standard models and constrain them.
Thank you. Wonderful. Thank you.
Hey, Saurabh. Good to see you. Great talk. I have several questions, but I limit myself to 2, and I can take them offline. And I haven't. Your paper is on my to-read list, so apologies if I should know the answer already. but I'll ask anyway. So I'll pick up in this question at the end. So you didn't go through the exercise of essentially assuming, let's say, the standard Gaussian absorption and just place an upper limit on the amplitude rather than simply ruling out the edges model. Did I understand it correctly?
Precisely, yeah. So we have not gone to an exercise of constraining different Gaussian-like features. Yeah.
Okay. So in that sense, you don't have, let's say, an upper limit on what the more standard model. Sure, probably unlikely anyway, but you don't have an upper limit of what a more standard model could be. Not yet,
right.
At least.
Yeah.
Okay. A second question, if you can go back to your slide where you showed the efficiency, sorry, correction before and after radiation efficiency and so on and so forth. Red and blue curve. I don't really have a feeling for what eta rad ought to be on how you get that. Can you elaborate on that? How do you measure that? I assume you do, right?
Right. So it's tricky. So eta rad is basically the radiation efficiency, and it's basically like what fraction of the power goes into the sky versus going into the water or into the ground. There is no direct way to measure it. So basically, we measure two different things. One is the total efficiency, which is basically this entire product, which is radiation efficiency times the impedance mismatch in the antenna. So this is basically done by taking our data and regressing it against the different sky model predictions, and with error bars because different sky models have different predictions. And the second quantity that we measure independently is just the impedance mismatch. So let me go back to the slide I probably skipped before, which is the setup. So essentially replacing the antenna receiver, sorry, the analog receiver with a very custom built S11 measurement unit. We had measured this impedance term to a very good accuracy. And based on that, we can then get our gamma rad or eta rad. But then what we are correcting for is the total efficiency right here.
But how about the water contribution, if I can still ask this?
Yeah.
How do you actually get that?
Right. So the eta rad is
I assume you do. No, I'm talking about the third.
This one?
The third term on the right. Yes.
Yeah. So this is derived from measuring the total efficiency separately, and then the 1 minus gamma square or the impedance term separately, and this is like a derived parameter out of the two. So
and your feeling is how uncertain is that? Because the correction is significant, right?
Right. So actually, the corrections have error bars on them. So what we do is one part of this error comes from just how sensitive we are to a specific sky model, right? So we use GSM or GMOS and how much it changes. And the second error term comes from night to night variations. So if we do the same kind of characterization over different nights, how much of the variation do we see? So actually on this specific plot, the leftmost column, the different colors basically show the kind of error bars that we have on these corrections. And this all gets into our systematic error contribution in the later parts of the analysis.
Thank you. Very nice. Thanks.
Yeah, thanks for the nice talk, Saurabh. I just wanted to check, in terms of your future plans, like what's the limitations in terms of your upper limits? Obviously, you say you can get more sensitivity. So, are you planning to redo the observations that you've done already, on the lake? And then, secondly, is it the instrument systematics? Is it the RFI or the ionosphere that's kind of limiting, improving your statistical constraining power?
Right. So currently our biggest limitation is the usable frequency band, because the kind of sites we have deployed for this result are not necessarily radio quiet. So any data before 55 megahertz or after 85, because FM band starts very quickly, we basically could use only this band, which was sufficient for this, but not for standard models. So our urgent priority is to go to a site that allows us to use more band, essentially. And that's what the plan for the summers are, to be going to Trans-Himalayas, which are much pristine and way more radio quiet. And we have observed there before as well. And at the same time, just observing for longer, given our flagging. So these two are the primary concerns right now.
Okay, thanks. So you are going to observe on the lake for longer to get more sensitivity. Yeah, okay, thanks.
Thanks for the talk, Saurabh. It was really excellent. And I just had a small question about the plot that you're showing right now. These spikes that you see in the jackknife tests, are these like present in the data, or are these an artifact of this analysis that you're doing here?
No, these spikes are real. And these spikes come from, so what happens is different frequencies have different integration times. So basically the spikes show the frequencies where majority of the time has been flagged due to RFI. So this is basically a noise that has a larger variance than the rest.
Okay, okay. So it's because of the RFI flagging which preferentially like throws away some frequencies than others.
Precisely. So the integration time per frequency is different.
Okay, thanks. And another question that I had is like, you have a reflection loss measurement system there, but then given that all commercial VNAs are able to maybe like measure the reflection coefficient accurately 10 to the maybe 40 dB or 50 dB, like is it sufficient for your analysis and get to the level of residuals that you'd like to be?
Right. So what our experience has been, if we just take the typical field fox VNA and go ahead with measuring with a very normal setup, we do not get below 10⁻³ accuracies, which is definitely not sufficient for our science. So basically this setup is kind of customizing the existing VNA with manual switching between open load, basically a manual calibration instead of the internal calibrations to have more control. So overall, like there have been very fine changes in this setup, so that the 10⁻³ gets to 10⁻⁻⁶.
Okay. And you only have a standard open short load, or is there also like 100 ohm or something like that?
No, just the standard loads.
Okay, okay. And also like this is a question related to your future deployments. Maybe it's a follow-up to Kavi's thing question. Like given that, see, you are already like radiometer noise limited, right? Like you are already below the radiometer noise limit that you would require to detect the global towards negative signal. And given that what you are limited by is systematics, in the long run, like even if you keep observing for days together, your systematics are not going to like change much on average. So like what techniques do you have to sort of handle the systematics better in the coming experiments?
Right. No, actually, for the current deployment, with the choice of our foreground and systematic model, we are actually thermal noise limited. So we have done a lot of tests to test the Gaussianity and how consistent we are. Actually, let me show you this plot. This panel here, this B panel shows the residuals. And once we correct for different integration times for different frequencies, we get the bottommost panel. And this is basically in units of sigma. And what we find, it is extremely consistent with Gaussian. So what we have overlaid here is the histogram of this along with the Gaussian. So yeah, so basically given that we are thermal noise limited, it makes sense to just observe more and beat it down.
Yeah, okay. Thanks, Saurabh.
Hi, that's quite an interesting choice of ground plane. Do you have any problems with motion in the water in your telescope?
Sorry, a problem with?
The water moving around, you know, or the telescope moving on the water. Does that have any effect?
Yeah, I mean, that's certainly a problem. And we have taken some cares of, let me go back to this slide. So essentially, what we are most concerned about in these kind of deployments is toppling, not just a toppling, but waving of the antenna, because that introduces a lot of beam chromaticity in the response, which we would like to avoid. So, so first, of course, is the wind conditions and how placid the lake is, so that feeds into our site selection. And then we have some mechanism to basically fix the antenna right at one place, so it doesn't drift over time. So with all those considerations, with this specific deployment, we did not have a problem with motions. But that is one of the reasons why we can't go to, say, lakes that have waves and all, because that will compromise the stability of the antenna itself.
Yeah, if not, I think we'll thank the speaker again for a great talk. That was really very interesting. Thanks, Saurabh. And congratulations on all those nice results. Cool. Well, I think that's it for the day. Thanks, everyone. And we'll see you next week.
Thanks.